So in the last few videos, we discussed very specific rules for differentiation, probably the most common ones you're going to have to use. So if you're not sure what I'm talking about, make sure you watch those previous videos. Now today, we're going to start getting into the more specific derivative rules, starting with the exponential rules. So let's say you wanted to take the derivative, d dx, of n to the exponent x. Now in this case, x is the variable. It's the thing that we're taking the derivative with respect to, right? And n is a number, right? So an example of this would be, 2 to the exponent x. That could be your function. F of x is equal to 2 to the exponent x. That's what we're talking about. So this is very different than a power rule where the variable is in the base and the number is the exponent. Now we have a number as the base and the variable in the exponent. So how do we take the derivative of this? Well, according to the exponential rule for derivatives, all you have to do is say that it's equal to n to the exponent x multiplied by the natural logarithm of n, whatever that base is. So in this example down here, if I have the function f of x equals 2 to the exponent x, and I wish to find f prime at x, the derivative of that function, my answer is simply going to be 2 to the exponent x multiplied by the natural logarithm of 2. And if this is confusing you, remember, if you take the log or natural logarithm of a number, that just gives you a number. So natural log of 2, or ln of 2 if you like to say ln, this is just a number. This is something that you can calculate. You can think of it as a coefficient if you want and put it on the front of your answer. It doesn't really matter. So this rule is pretty basic to apply, right? I'll show you one more example, even though I don't think you'll necessarily need to see it. You just have to understand the pattern, right? F of x is equal to, let's do 4 to the exponent x. Okay? And let's say we want to find f prime at x. All right. Well, the answer is going to be 4 to the exponent x. It starts off the same. Multiply by the natural logarithm of 4. And you do have the option here. You can put the 4 in a bracket next to natural log, but you can also just leave it like I did the previous example. You can just leave it natural log of 2 like that. You don't need to include the bracket. Now, you can apply this rule in combination with other rules, just like we've talked about in previous videos, right? So let's say, for example, we had the function f of x is equal to 3 to the exponent of x squared. So now things look a little bit different, right? We have what is most generally an exponential, right? It is a base that is a number to the exponent of something that has a variable in it, right? So most generally speaking, on the outside of this function, it is an exponential, and we would use the rules we just discussed. However, in that exponent, we don't just have x, we have something that is more complicated than x. And so if you've watched the previous videos, you know this is where we apply a chain rule. So let's take the derivative, f prime of x is equal to, and we'll start with the exponential rule, right? The answer will simply be 3 to the exponent x squared multiplied by the natural logarithm of 3. However, it is not simply x in the exponent, so we must multiply all this by the derivative of that inside function, the function where x normally is. So what's the derivative of x squared? Well, it would be 2x. And if you'd like to put the natural logarithm of 3 in a bracket to distinguish it so it doesn't look like you're taking the natural log of 3 times 2x, just to keep it organized, right, and to avoid confusion, you could absolutely do that. It's up to you. Okay, let's look at another example. Let's say we have f of x is equal to, and let's say we have something like this. Let's do 2x to the 3 plus 4 to the exponent 2x, something like this. Well, if we take the derivative, we know that when you have an expression like this with multiple terms, that you can take the derivative of each term individually, just like when we were doing the polynomials with the power rule. So you start by taking the derivative of this first part, 2x cubed. That will give you 6 2x squared. If you don't remember how to do that, watch the power rule video. But in essence, you just take that 3, multiply it by the 2, that gives you 6, and the exponent 3 reduces by 1, it becomes 2. Now, what about the second term? This one's a little more complex, right? It has the variable in the exponent, meaning this is an exponential, so we're not using the power rule. So what's the derivative of an exponential? Well, it's simply that same term multiplied by the natural logarithm of the base, which in this case is 4. However, that exponent wasn't just x, it was something more complicated than x. So we have to multiply by the derivative of that, right? This is your chain rule. What's the derivative of 2x? Well, it's going to be 2. And so without simplifying anything any further, this would be your final answer. So you can see that you can have chain rules interacting with the exponential rule. You can have power rules and exponential rules together. You could even have a product rule or a quotient rule question where you have an exponential somewhere in that equation. So most of the time when you get to the more challenging questions, you're going to have to use all of these rules, or at least several of them, depending on what you're given. Now let's look at a special case of the exponential rule. Let's say we wanted to take the derivative of e to the exponent x. Now this is a special case of what we just discussed, right? Because normally it's n to the x, where n is a number. And e, if you don't remember, this is Euler's number. That's a very special number in mathematics, right? If you don't remember, e is equal to approximately 2.178, and it's a running decimal, it continues. And if you don't remember where that comes from or why it's relevant, you can watch this video here. But nevertheless, when you take the derivative of this, if we try to use the same rules as before, where we say, okay, a number to the exponent x, when you take the derivative of it, becomes that same expression multiplied by the natural logarithm of that base. Well, what is the natural logarithm of e? Well, the natural logarithm of e is just 1. So we don't need to write natural logarithm of e, which is why this rule simply looks like this. The derivative of e to the x is equal to e to the x. If you forget why the natural logarithm of e is equal to 1, remember, natural logarithm is simply log with a base of e. It's a logarithm base e. So if you take log base e of e, of course it has to equal 1, because e to the exponent 1 is equal to e. Anything to the exponent 1 is equal to itself. So whenever you take natural log of e, of course you're going to get 1. So this is a special case of that exponential derivative rule. And if you forget about logarithms and natural logarithms and you want a refresher, you can go watch this video here. Okay, let's now do a couple examples. And I'll try to make them interesting, since obviously taking the derivative of e to the x is going to give you e to the x. So let's say we have the equation here, f of x is equal to e to the exponent, we'll do 3x squared plus 2x plus 1. So it's a base of e, it's an exponential with a base of e, but in that exponent we have an entire polynomial, not simply x. We have a long polynomial, it's actually a trinomial. How do we take the derivative of this? Well, again, most broadly speaking, this is an exponential, right? It's only within that little exponent where the x usually is that we have something more complicated. So of course this is going to be a chain rule. So let's take the derivative of e to the exponent something. It always gives you e to the exponent something, right? That same thing. So we start like that. But again, that something in the exponent is not simply x, so we have to multiply our answer by the derivative of that thing. That's our chain rule. What's the derivative of that? Well, I think we know how to do that. It would be 6x plus 2. Right? If you forget those power rules, remember, go watch the power rule video. Now that we've talked a bit about the exponential derivative rules, we also have to talk about the opposite of that, right? The other relationship, the logarithmic expression. Because for every exponential equation that exists, there's also a logarithmic expression that exists. So let's say you wanted to take the derivative of log base n. I like to say log, but it's logarithm base n of x. How do I take the derivative of this thing? Well, all that's going to happen is it will become 1 over x multiplied by the natural logarithm of that base n. And there are various proofs as to why this kind of thing happens. I might make a video on that one day. But for now, just know that this is the rule. So if I have f of x is equal to log base 10 of x, I'll use base 10 because that's just a common base that we use for logarithms. The answer, I shouldn't put equals here, sorry. I should say when I take the derivative of this, so this is f of x, if I wanted to find f prime of x, my final answer would be 1 over x times the natural logarithm of 10. And that's it. So this is one that you just kind of have to remember the rule, remember what it looks like, and you can substitute the values where they're supposed to be. The base of 10 goes right here. And of course, this is a rule that you can use in conjunction with the other rules, just like we've been discussing. So let's say you had, for example, f of x is equal to, let's do something a little bit different now. Let's do x squared times log base 10 of x. Well, we have an x squared, normally that could be its own function, and we have log base 10 of x, which typically could be its own function as well. So when we have these two things multiplied together, of course, that will be a product rule. So if I want to find the derivative, remember what our product rule is, right? The derivative of the first times the second plus the first times the derivative of the second. So let's do that. F prime of x is equal to the derivative of x squared, which is 2x multiplied by the second part, log base 10 of x, plus the first part unchanged, which is x squared, multiplied by the derivative of the second part. This is where we're applying our new rule. What's the derivative of log base 10 of x? Well, it's 1 over x natural logarithm of 10. And if you wanted to, instead of multiplying these things like this, you could simply put the x squared on the top of this fraction. Or in other words, you could say x squared over x natural logarithm of 10. That kind of makes it look a little bit neater and a little bit nicer. So I would do that. Okay, we'll do one more for this one. Let's say you have f of x is equal to, and let's say we have log base, let's do base 4 just to change it up, of and then we'll do a bracket here. We'll do 2x squared plus 3x. And we want to find the derivative, of course, f prime of x. What's the derivative of this? Well, again, most broadly, right, on the outside, we would say this is a logarithm, right? So how do you take the derivative of a logarithm? You simply say 1 over, usually it's x, right, whatever this thing is. So I'm going to put that thing first, 2x squared plus 3x, multiplied by the natural logarithm of the base of 4. Right, that follows the pattern. However, this thing here, that usually is just x, is something more complicated than x, meaning we have to use our chain rule. We have to multiply by the derivative of that thing. What's the derivative of 2x squared plus 3x? Well, it's 4x plus 3. And of course, to make this look a little bit nicer, you could say, let's put this 4x plus 3 on top of the fraction. 4x plus 3 all over 2x squared plus 3x. I'll put that in a bracket because it's all being multiplied by the natural logarithm of 4. And I would say that is my answer. Now, just like for exponentials, where you have the general rule where you have a base of n, and then there's a special version or a special case where you're using a base of e, the same sort of dynamic happens with the logarithmic functions. So where you can say you have log base n, you could also do this with log base e. Log base e, of course, we know is the natural logarithm. So natural logarithm of x. If I wanted to take the derivative of this, we can think about what it would normally be for a log base some number, because remember, ln of n is the same as saying log base e, right? Log base e of x. What do we normally do? Well, normally we would say it's 1 over x times the natural logarithm of the base, but the base is e, right? The base is e in this case. Natural log of e is just 1, so it goes away. So instead of bothering with all that, we can simply say the answer is 1 over x. So the derivative of the natural logarithm of x will equal 1 over x. So just like in the exponential where you have a base of e, the derivative is much more simple. The same is true when you have the derivative of the natural logarithm of x. It's much more simple than when you do log of a different base. So if I was going to give you an example, say f of x is equal to, we'll do natural logarithm of, let's make it x squared, something like that. Well, to find the derivative, typically the answer would just be 1 over that x, so 1 over x squared. Because this x squared is more complex than x, we have to multiply by the derivative of x squared, which is 2x. And I could simplify this nicely by putting that 2x on the top of my fraction, so 2x over x squared. And if you would actually like to, you could simplify this even further. Because there's an x on the top and bottom, which would cancel out, you would have 2 over x. You could even say that that's your final answer if you're interested in simplifying further. So hopefully that clears everything up with regards to the exponential and logarithmic derivatives. As you've seen, you can use them in combination with all the previous rules, so make sure you're familiar with the rules up to this point before you move on. And then we're going to take a look in the next video at the next type of derivative rule.